So the alternative formula for curvature, it's easier in many other cases, because although, well, let's have a look at this. Even though it involves a cross product, which I'm not gonna lie, it takes a good minute to go, but it's easier in many situations like the one we're gonna do. So. Well, so let's use the alternative curvature formula to compute the curvature for the curve given by this vector valued function. Then find the curvature at the point 8, 2, 2. All right, so let's review the formula for curvature, the alternative formula. What do we need? V cross with A, the magnitude of V cross with A divided by the cube of v of t, that is the velocity vector. So that let's have a look at that example. Okay, so let's find the velocity vector. That is, well, the derivative of 2t squared, that's 4t. The derivative of t, that's a 1, and the derivative of 1/2 t squared, that's just t. All right, find the acceleration vector. That equals, what's that? 4, 0, and 1. So we need to find the cross product between these two vectors. And by the way, because you may see it in a different way in my lab or in other resources, other textbooks or online exercises, you may see the numerator v cross A as A cross V. Well, let's talk about that cross product. Recall that when you do the cross product of two vectors in the reverse order, all you get is the same vector but with the opposite in sign component. All right? But in this case, well, since we're taking the magnitude of that cross product, well, that's not going to matter because that's going to get positive, and that's going to be a positive number, a positive quantity, if we will. So either way you do it, that's fine. But still, I'm going to do V cross A. So V cross A, velocity cross acceleration, and that'll be, so I, J, K. And I'm going to write the vectors as rows: 4t, 1t, 4, 0, 1. All right. Well, this time I'm not just going to give you the result for this cross product. I'm going to do the whole thing this time, because this is the first time we will do a cross product between two vectors where the vectors are variables. So you might want to see how this works. All right. So let's see. So let me repeat the first two columns. So let's do. Okay, the product of the diagonals in the product of the main diagonals, that is I times 1 times 1, that's simply I. And then J times T times 4, that's simply 4TJ. And lastly, for the main diagonals, K times 4T times 0, that's just 0. Okay, so that's the product along the main diagonals for the right ones. Okay, then minus the product of the secondary diagonals. That is J times 4T times 1, that is another 4T J. Oh, it's also J, right? So, and then what's the next one? I times C times 0, that's just 0. K times 1 times 4, that's 4K. All right. Well, the result for this, that's going to give us I, which is just I. The J's get canceled because 4TJ minus 4TJ get canceled, plus, or rather minus 4K. Which in component form, which is more convenient, that'll be 1, 0, negative 4. So that is the cross product between the two vectors. Alright, so now let's find the magnitude of that cross product. That's going to be the numerator. Okay, so the magnitude of v cross a, that is the square root of 1 squared plus 0 squared plus negative 4 squared, that equals, okay, the square root of 1 squared, that's just 1 plus 0 plus 16, 17. That's the square root of 17. So that's the magnitude. So we already have the numerator. Let's get the denominator. For the denominator, we need to get the magnitude of the velocity vector. That is, let's go back to v of t and find its magnitude. That is the square root of 4t quantity squared plus 1 squared plus t squared. Careful when squaring this 4t. The square affects both the coefficient 4 and the t as well. That is 16t squared plus 1 plus t squared. And combining like terms, that's the square root of 17t squared plus 1. So we have everything we need in order to find or to express the expression for the curvature for every value of t, as long as it is in the domain. And well, if we look at this vector valued function, well, it's defined for all values of t. We have polynomials. I mean, there's no restricted functions here, so it should work for all values of t. So let's express the kappa of t equals the magnitude of the cross product between the velocity and the acceleration divided by the magnitude of the velocity, but cubed this one. Alright? This gets cubed. That means all we do is substitute the square root of 17 in the numerator, and in the denominator that's the square root of 17 t squared plus 1. Careful, we are raising all the denominator to the third power. So you don't want to leave it like this. You might want to use our rational exponents here. That is, okay, exponent, and then we have the index of the radical, which is an invisible 2. That is the square root of 17 over 17t squared plus 1 to the 3/2. So that is our expression to find the curvature for that vector value function for that curve at every single value of t. Alright? So let's see. There's a part B to this problem. They're asking us to find how fast the curve turns at the point 822. Alright? Well, I mean, look at this expression. This is an expression in terms of t, but they're giving us an order triple. We're not going to substitute an order triple. So first, what we're going to do is find when is the particle at the point 822. So what do we do? Well, so we can write this vector valued function in terms of a set of parametric equations. So I'm going to do that on the next page. I left some space to do that on the next page. So let me write it in parametric form. So we have x equals to 2t squared, y equals to t, and z equals to 1/2 t squared. I'm going to set this components equal to, okay, so I'm going to set them equal to the order triple where we want to know the value of t for, which in this case is 822. That is x, y, and z. So that's going to give us, so let's set this 8, 2, and 2. So that's going to give rise to 3 equations here. Well, actually, one of the, how can I put this, shortcuts, if you will, it's to only solve the easiest equation that you see of the 3, but you want to make sure that you don't get more than one value of t for the different point, because it is possible that a curve goes through the same point at different times. In this case, I think it's clear that it's just going to go once, only when t equals to 2, but still you want to make sure there's no other points. So 2t squared equals to 8, t equals to 2, and 1/2 t squared equals to 2. So that is t squared equals to 4, and t equals plus or minus 2. T equals to 2, it's just t equals to 2. And lastly, multiply both sides by 2 to get t squared equals to 4 t equals to plus or minus 2. So in this case, again, we will take the value of t that repeats for the 3 of them. All right, so that means the particle is at the point 8, 2, 2 when t equals to 2. Right, let me make some space in here to find the curvature at that value of t. Okay, so all we do is go back and use the result we got from before. That is kappa of 2 equals to the square root of 17 divided by that is the square root, no, not the square root, it's, well, yes, that's fine. That's 17 times 2 squared plus 1 raised to the 3 halves. And well, what is that? 2 times 2 equals to 4. 17 times 4, that's 68 plus 1. That's going to give us a square root of 17 over 69 raised to the 3 halves. And well, since that number, it's not a perfect square, we just leave it like this, all right? I mean, you could potentially factor out a 9 times 7, and then, well, that's just going to complicate the problem a little bit. You don't need to get the extra amount. That's fine. Again, when it comes to this kind of results, my MATLAB, it's very lenient about it. It's not like in your intermediate algebra course where you had to input your results in a rationalized form and simplifying the radicals to lowest terms. All right? Okay, now just be careful because we may apply this to curves in the plane. I mean, because curves in the plane have curvature, not just curves in space. And again, let's recall that we cannot perform the cross product for a curve for vectors into dimensions because again, check this out. I and j and say 1, 3 and 0, 1, we cannot find the determinant of a 2 by 3 of a rectangular matrix. The determinants are defined for square matrices. So in this case, the trick is to make the third component equal to 0. Just put a couple of zeros in there. Otherwise, we wouldn't be able to find the curvature or the cross product, right? Okay, let's move on to finding the principal unit normal vector. Okay, again, curvature is going to describe how fast a curve turns, but we also want to know the direction in which the curve turns. Well, we're going to find out by means of what we call the unit normal vector, or the principal unit normal vector, which is defined by this equation. So what is this? Okay, so it's the derivative of the tangential divided by its magnitude. Although it looks like a very innocent formula, if you will, well, that's going to be that's going to take a while for the example we're going to look. So to give you a picture, okay, so we have a curve right here. Could be in space or could be in the plane. Let me just think of the curve in the plane. Okay, so direction. First of all, if we have a curve going in this direction, so that means the tangent vector, it's always going to point in the direction of the curve, that is in the direction of increasing values of t. While, well, in this case, the unit normal vector will always point towards the concave side. That is, let me label this, big T. On the other hand, it's going to point, the normal vector is going to point towards the concave side. That is, towards this side, the inside part of the curve, if you will. We don't call it the inside, it's the concave side, right? Well, so not the outside. For instance, we have another example. Well, let me make another curve here. like this. So at this point, for instance, of course, I need a sense of direction, right? Otherwise, so that means tangential at this point and unit normal vector in this direction. Tangential in this direction, unit normal in this direction. Again, the yellow vectors, which are the tangential vector, the unit tangent vectors, point in the direction of increasing values of t, or increasing time, while the unit normal vector are going towards the concave side. All right? Okay, so let's have a look at this example, and let's get ready to do a lot of calculus today. So let's find the unit normal vector for the curve given by 2t plus t squared. That looks like a very cheesy curve, right? Looks like it's going to take just a couple minutes to go, but it's not going to be. You'll see. All right, so let's go about finding the unit normal vector, and we will evaluate that unit normal vector when t equals to 1. So first of all, to begin with, we need to get we need the derivative of the unit tangent vector. Well, that means we first need to find the tangential. So how do we find the tangential? Well, let me write it down here. So the tangential, that is r prime over its derivative. I mean over its magnitude rather, not the derivative. So let's get r prime first. That is the derivative of 2t, that's 2. The derivative of t squared, that's 2t. Okay? Let's get its magnitude. Let's get the magnitude, that is the square root of 2 squared plus 2t quantity squared. That is the square root of 4 plus 4t. So, and actually, guys, when you are working on a problem like this, here is where my advice is to simplify as much as you can. In this case, notice how we can take out a factor of 4, which is a perfect square. That is 4 times 1 plus t squared, and which reduces to 2 square root of 1 plus t squared. Right? Yeah. Trust me, it's going to be a lot better. Unless you have a number that is not a perfect, well, even if it's not a perfect square, take it out as a radical, as the square root of the number, because when we do the calculus for this, it would be better to have those coefficients and avoid many chain rule problems here. Okay, so we're ready to find the unit tangent vector here. All right, so the unit tangent vector, that is the derivative of r, which we just found, divided by its magnitude. So that is 2t divided by this radical, 2 square root of 1 plus t squared. So in this case, yes, we will need to distribute the denominator over the two components of the vector, because we need to simplify them as much as we can before we keep doing the calculus to get the unit normal vector. All right, so in this case, 2 over 2, the 2's cancel. That's going to leave us with 1 over the radical, 1 over square root of 1 plus t squared, comma, the 2's cancel again here, and that's going to leave us with t over the square root of 1 plus t squared. All right. And actually, oh guys, you know what? I need to fix a little issue here. The original function must have a negative here, otherwise it's not going to work. So let me make a couple of changes here. Minus, well, this one becomes a plus, that's a minus, and that becomes a minus. All right? Okay. So So that's how we get the unit tangent vector. So plug in your favorite value for t, you will get constant vectors whose magnitude are going to be equal to 1. So now we need to get the unit normal vector. How do we get that? Okay, let's go back. We need the derivative of the tangential, that is that humongous mess we just found, and divided by its magnitude. So, okay, that means we need to differentiate these two components. For the first one, we're going to need a chain rule. For the second one, we're going to need the quotient rule. All right, okay, I'm going to use different colors to differentiate these two. I'm going to use green for the first component. So, that is the derivative with respect t of the quantity 1 over square root of 1 plus t squared. That equals the derivative with respect to t. Well, in this case, you can't differentiate this expression, this function rather, while you have the radical in the denominator. Make it a rational exponent and still move it to the numerator with negative sign. That is the derivative of 1 plus t squared to the negative 1/2. All right. So we're ready to differentiate by chain rule. That equals negative 1/2 1 plus t squared to the negative 3/2 times 2t, again by chain rule. Now see how these twos are going to get canceled. I'm going to rewrite that negative exponent as a positive exponent. That's going to leave us with the following, that is negative t over 1 plus t squared to the 3/2. So that is the derivative of the first component. For the second component, let me use a different color. That is to differentiate this quotient right here. So, okay, let's recall our quotient rule. So whenever we have a quotient between two functions and we want to differentiate, that's going to be u prime v minus v prime u. Everything divided by the denominator v squared. All right, so let's apply this to this quotient. But first of all, we need to rewrite it like, actually, let me do that right here. We write it with rational exponent at once. All right, so let's go and differentiate this. Okay, the derivative of the numerator, which is the derivative of negative t, that's simply negative 1, times the denominator without doing anything, that is 1 plus t squared to the 1/2, minus the derivative of the denominator, that is the derivative of that baby, what is that, chain rule. So that is, I'm going to do 1/2 1 plus t squared to the negative 1/2. Okay, take one, subtract one integer to the exponent, and then multiply by the inside, that is 2t. Okay, but that's just v prime. Don't forget to multiply by u, which in this case is negative t. Everything divided by 1 plus t squared to the 1/2 squared. Recall that we're squaring the denominator. Right? Let's see. So let's simplify all this as much as we can. So here I'm gonna go back to radicals first of all. I'm gonna cancel these coefficients. Those two are gonna go away. T times t, that's gonna become t squared, and negative times a negative equals to positive. So number one. So I don't think I'm going to have enough space here. Let me go here. Okay, so that'll be negative 1 plus t squared to the 1/2 plus t squared over 1 plus t squared to the 1/2. Everything divided by squared, power half, they cancel out because power of another power, multiply the powers, 2 times a half becomes a 1. That's just going to leave us with the following. 1 plus t squared. Simply 1 plus t squared. Well, so here we're still expected to simplify this to lowest terms. How we're going to do that? Well, it turns out that we have what? A complex rational expression, that is because we have fractions containing a big fraction. And also I'm going to change those rational exponents back to radicals. So, and I'm going to use a different notation for this, so it's easier to read. So I'm going to go like this. I'm just going to write the numerator. So negative square root of 1 plus t squared. Alright. And I'm going to leave a space. I'll show you why. That is plus t squared over the square root of 1 plus t squared. Okay. So the reason why I left... Oh, hold on. Do you guys agree? Dividing. Okay, this division can be written like this. Divided by 1 plus t squared. Everything by 1. I know that 1 is a little silly, but it's easier to read this quotient between these two crazy expressions. All right, so I'm going to write this invisible 1 right here, so we can combine the two fractions together by finding a least common denominator. All right. So that means I'm going to multiply numerator and denominator by the square root of 1 plus t squared. 1 plus t squared. So we will now be able to keep simplifying this derivative. All right? So, all right. So what is this? Okay. So we have the same radicand. Right? We can, essentially we're multiplying 1 plus t squared. By itself, the radicals actually just cancel. That's going to leave us, well, number 1, this is negative 1 plus t squared plus t squared, everything divided by the square root of 1 plus t squared. Right? That times 1 plus t squared over 1. I know this over 1 might look a little silly, but we need this so we can easily see how are we going to cancel this out. All right, so let's, yes?
Did you mean to put a division sign between those two brackets?
Yes, division sign, yeah. Thank you. All right, so in the next step, well, I'm going to distribute the negative, right? The negative, that's going to be negative 1. Negative 1 minus t squared plus t squared over the square root of 1 plus t squared. Okay? Now, I'm going to change this division into a multiplication by flipping the second fraction. Maybe you've heard about the KFC rule. Have you ever heard of the KFC rule? Yes? For those of you who haven't heard about the KFC rule, well, no, it doesn't have anything to do with chicken. KFC, that means keep, flip, change. So that's what we use when we're dividing rational expression. That is, keep the first fraction, flip the second fraction, change the division symbol with the multiplication symbol. So that's the KFC rule. All right, and we're almost done here. Well, with the derivative, of course, not with the problem yet. So t squared minus t squared cancel out. That's going to leave us with a minus 1, with minus 1 over the product between. Okay, I'm going to change this radical back to rational exponent. I'll show you why. Because I would like to combine this into a single term in the denominator. Notice how we have the same base. All we do is add the exponents. A half plus 1, that's negative 1 over 1 plus t squared. Everything raised to the 3/2. So this is how it reduces to lowest terms. All right, so we're ready to express the derivative of the tangential. That is big T big T prime. That is what we got for the derivative of the first expression, which is negative t over 1 plus t squared to the 3 halves, comma, this result, negative 1 over 1 plus t squared to the 3 halves. So that's only the derivative of the tangential, all right? So we're almost there, so to speak, to get the unit normal vector. Now we need to find the magnitude of this vector, because to get the unit normal vector, we need the derivative of this unit tangent vector divided by its magnitude. So, yep, let's get the magnitude of this. So that is the magnitude of big T prime, that is the square root of negative t over 1 plus t squared to the 3 halves squared plus negative 1 over 1 plus t squared to the 3 halves squared. Let's simplify all this madness here. Okay, negative square becomes positive, both negatives become positive. So for the first term, that is, that's going to be t squared. Okay, power 3 halves squared, that is 3 halves times 2. The 2's are going to get canceled, and that's going to leave us with a 3 only. With a power 3, that is 1 plus t squared to the 3rd power plus negative 1 squared, that's positive 1. And again, 1 plus t squared raised to the 3 halves, also square, cancel the 2's, we're left with the 3. 1 plus t squared to the 3rd power. Alright? Okay, well, the good thing here is we have the same denominator, so we may go ahead and combine. There's no need to multiply any numerators or denominators of any of the fractions by a missing fraction, so it's going to simplify really nicely, you'll see. So that's the square root of t squared plus 1 over 1 plus t squared cubed. And hopefully we can see that t squared plus 1 is the same as 1 plus t squared. So here we can reduce powers, right? I mean, think of this as an invisible power 1. 1 minus 3, that's negative 2, or 2 powers in the denominator, that is 1 over 1 plus t squared squared. And here we could use the quotient rule for radicals, that is the square root of 1 in the numerator, which is simply 1, and the square root of this quantity squared, which is simply 1 plus t squared. All right? So that is the magnitude. That's a magnitude of the derivative of the unit tangent vector. So we may go ahead and find the unit normal vector. Okay, let's express the unit normal vector by writing the quotient n of t. That's big T prime of t divided by its magnitude. All right. So, okay, so that's the derivative. That is what we got over here. Oh, I'm going to need more space. That is this huge vector here. That is negative t over 1 plus t squared to the 3 halves, comma, negative 1 plus t squared to the 3 halves, divided by 1 over 1 plus t squared. Okay, yes, we need to simplify this to lowest terms, of course, alright? So let's have a look at this. Well, so, instead of dividing, I'm going to multiply by the reciprocal. That is like the KFC rule, if you will. So I'm going to go like 1 plus t squared times the components of this vector, that is t over 1 plus t squared to the 3 halves, comma, whoops, let me make more space first, and that is, comma, negative 1 over 1 plus t squared to the 3 halves. All right. Okay, so let's distribute this. We'll distribute the 1 plus t squared to the numerator of both vectors. That is negative t times 1 plus t squared over 1 plus t squared to the 3 halves, comma, negative 1 times 1 plus t squared. Everything divided by the same 1 plus t squared to the 3 halves. Well, again, we will be able to reduce a lot because we have that 1 plus t squared to the first power with that 1 plus t squared to the 3 halves. So that is 1 minus 3 halves, 1 minus 3 halves, that is 2 halves minus 3 halves, that's a negative 1 half, which means a 1 half power in the denominator. So that is negative t over 1 plus t squared to the 1 half, comma, negative 1 over 1 plus t squared to the 1 half. All right. All we need is express this in radical form. All right. T over the square root of 1 plus t squared, negative 1 over the square root of 1 plus t squared. So that is our unit normal vector. So this vector in variable form will give us all the vectors at every single value of t that are pointing in towards the concave side of the curve, not in the direction of the velocity. That's the tangential. Now, in this case, the normal, it's going to go in the direction of the concave side. All right. Well, they're also asking us to evaluate this for n equals to 1. All right, so n of 1, that is negative 1 over the square root of 1 plus 1 squared, negative 1 over the square root of 1 plus 1 squared. All right, that is negative 1 over the square root of 2, negative 1 over the square root of 2. So let's make sense out of this result. Okay, this should look like a unit vector. I mean, look at the numbers. Negative 1 over root of 2, negative 1 over root of 2. If you rationalize those denominators, you get the famous roots of 2 over 2 that are the what's it called, the cosine and sine values for the 45-degree angle in the third quadrant, right? Those are numbers, those are components in the unit circle, right? So somehow it makes sense, unless you're working on a vector valued function for which these vectors do not look like unit. At first glance, just take the magnitude and it should give you a 1. All right, well, how about we get a visual of this? Okay, I'm going to go to the graphing calculator and let's go in parametric mode. Okay, so let's see, mode. Yes, I'm still in parametric. Let me clear everything I have. And let's go and type in our vector valued function here. All right, so let's see, that was 2t. And minus t squared, negative t squared. And let's graph. Right? And let me graph. Okay, let me do negative 5 to positive 5, just to get a more symmetric graph. So that's going to give us an upside down parabola. And well, how does that make sense? I mean, look at the parametric equations, or at the vector valued function. That is, okay, let me go backtrack a little bit. So that means x equals to 2t and y equals to negative t squared. Well, so look at this y minus t squared. If you eliminate the parameter, that is, yeah, let me get rid of this for a second. That is t equals to 1/2 x. Y then will be negative 1/2 x quantity squared, which is negative 1/4 x squared. Isn't that describing a parabola upside down because of the negative coefficient? Alright, so now I need to know what's the point when t equals to 1. Well, for this I'm going to go to second graph to look at the table. So when t equals to 2, I get the point for negative 4. Alright, so okay, let me click on graph, trace. Let me do t equals to 2. Okay, it's going to take a minute to go. Oh, that's because our t step. Okay, let me do steps up one at a time. Okay, so trace. There you go, much easier. So that's going to give us this point right here. All right, so I'm going to graph, I'm going to sketch, I'm going to do a rough sketch of that function on the notes. Back to the notes. And just to make sense out of this, okay. So that is our upside down parabola, and well, direction matters here, right? For parametric equations, for vector valued functions, direction matters. I'm going to go to the point 2, negative 2. Was that the point? Let me go back again and look at the table. So, hey, why is not showing? Oh, there you go. So, table, second, table. Yes, 4, negative 4 actually, not 2, negative 2. Okay, so that's this point essentially, right? So, what do we have? We have the tangent vector pointing in this direction. Now, what are the components of the unit normal vector? Well, from the geometric point of view, the unit normal vector should point in the direction of the concave side of the parabola. That is, in this direction, right? How does that make sense with the result we just obtained? Look at the signs of the components of the unit normal vector when t equals to 1. That's negative and then negative. Does that look about right? Negative and then negative? It should. So this is a good way to verify your work. Number 1, taking the magnitude of that vector you just got at the very end. Number 2, using a graphing utility to look at these vectors. If you're working on a vector value function in space, just use GeoGebra. Use the curve command to graph a curve in space. All right. So yes, that was only one example for finding the unit normal vector. All right. Yes, this gets crazy, right? Okay, let's have a look at more pieces of information about these vector valued functions, the tangential and the normal components of the acceleration. All right. Well, so here's the thing. In physics, in mechanics, whatever mechanics course, whether this is classical Newtonian mechanics, Lagrangian, Hamiltonian mechanics, so you would be looking at these components of the acceleration, because I mean acceleration, it's actually very important. It's a thing because it varies for every different planet, so to speak, if you will, right? So there's big studies about this gravity. So well, acceleration in general. Well, so it turns out that acceleration, which is again a vector that points towards the concave side of the curve. However, if you will, here, so this vector A is going to cast a shadow onto onto the tangential vector, but it's also going to cast a shadow onto the normal vector. So that means what we're going to do, we are going to find what we call the normal component and the tangential component of the acceleration. That is the shadow of the acceleration onto the normal and onto the tangential. And we express this as a linear combination of the two vectors. That is, the acceleration breaks up into two vectors. a portion of the tangential plus a portion of the normal. That is, that AT in A sub n, it's the length of the shadow of the acceleration onto number one, the tangential, and number two, the normal vector. Where here, so here we have the expressions to find those components. So those components are given by finding the dot product between the acceleration vector with the unit tangent vector. That's to get the tangential component of the acceleration, and the dot product between the acceleration and the unit normal vector. That's to get the normal component of the acceleration. That is to find how much of the acceleration projects onto the normal vector. Let's have a look at one example. Okay, so let's assess these formulations here. Number one, okay, so finding the acceleration, nothing too crazy. Just take the first two derivatives, right? Finding the unit tangent vector, nothing too crazy either. Take that first derivative we just got in the first part, for instance, and find its magnitude, and then divide that vector value, the derivative, by that magnitude we just found. However, when it comes to finding the normal component of the acceleration, oh, look at this. We need to find big N, right? And we just saw how intense it is to find big N, right? I mean, if you want to do it the way we did it before by using the unit tangent vector, we're going to get it anyway. So that's fine. Then you will have to do the unit tangent vector, the unit normal vector, by finding the derivative of this, take the magnitude, and then do a lot of algebra. All right? Well, luckily there's alternatives to bypass all that process, and here is where we have a couple of alternatives to find A sub n, because now, especially the second version, A sub n, which is V cross A divided by the magnitude of V. Be careful, you may not want to confuse this with the formula to find the curvature. It looks a lot like it, except that the curvature has a cubic here, not this one. Alright? So, alright, how about we look at one example where we will find the components of the acceleration, the normal and the tangential components of the acceleration, for a circular trajectory in this case. Well, so number one, okay, let's gather all the information. Okay, yeah, we have everything we need, by the way. So we're given a vector valued function, 2 cosine 3t comma 2 sine 3t. Well, what is this? This is a circle of radius 2, traversed. Well, it's not traversed twice. It's traverse, I guess, 3 times. No, not 3 times. Anyway, so it has a coefficient in the variable, which may affect the rate at which it goes around, or it traverses rather. Okay, so well, let's just do the calculus. Let's do r prime. That is, by chain rule, the derivative is 3 times 2. That's negative. The derivative of cosine, negative 6 sine 3t plus 6 cosine 3t. Okay, so that is the derivative. Let's also find the magnitude, because we're going to need this for the tangential. So the derivative, that's r prime. So the magnitude of r prime, that is the square root of negative 6 sine 3t squared plus 6 cosine 3t squared. That means, okay, the square root of 36 sine squared 3t plus 36 cosine 3t squared, right? And again, we have seen this identity many times. If we factored a 36, that's going to leave us with sine squared plus cosine squared. And because the angles are the same, the angles match in here, well, here we can simply reduce to a 1. The square root of 36 times 1, which is 36, that is simply 6. All right? Okay, so we're ready to compute the tangential here. So that is, oh, let's find r double prime. That is going to be, okay, velocity, acceleration. That is the derivative of sine, that's cosine, that's negative 18. Cosine 3t and negative 18 sine 3t. Okay, we're gonna need this later. So in the meantime, let's find the unit tangent vector, that is big T. Oh, just big T. That equals, again, r prime over its magnitude. So that is the first vector we got over here, negative 6 sine 3t, 6 cosine 3t, divided by the magnitude, which is 6, which will reduce to negative sine 3t cosine 3t. And well, of course, that should look like a unit vector because we have components that are either cosine or sine or cosine, it doesn't matter. And look at the coefficients. The coefficients are either positive 1 or negative 1. So that gives us an idea that these are indeed going to be unit vectors. Okay, so we have everything we need to find the shadow of the acceleration onto the tangential or onto the unit tangent vector. That is, let me call this number 1. So number 1, that equals a sub t, which is the acceleration dotted with the unit tangent vector. That is, we got the acceleration vector already, right? So that is the acceleration vector, which is the second derivative of r of t, that is negative 18 cosine 3t, negative 18 sine 3t, and dotted with what we just got for the unit tangent vector. All right, let's see. Negative sine 3t cosine 3t, okay, negative cosine 3t. So let's see, dot product, that equals, okay, negative 18 cosine times negative sine, that's 18 sine cosine sine 3t cosine 3t, minus times a plus, that's minus 18 another sine 3t cosine 3t. And combining like terms, this is going to be 0, right? We will make a geometric sense out of this. You'll see, okay? So that's just halfway through the problem. We just got the length of the shadow of the acceleration onto the tangential. Let's do part B, or number 2 of the problem. That is, now that's 2. That's the normal component of the acceleration. That is, in this case, the acceleration vector dotted with the unit normal vector. But again, do you feel like doing the unit normal vector? I mean, don't get me wrong. Actually, for this trigonometric vector valued function, it's not going to be as crazy as the algebraic one we just did. Because we will be going back and forth between sine, cosine, sine all the time. And we will get this Pythagorean identity that reduces to 1 a lot of times. So even if you do it that way, that's not going to be as crazy as the other one. However, the purpose here is to use one of the alternatives. And well, actually, typically one of the alternatives is easier than the second one. And actually, the second one, it's easier than the first one. Because look at the first one. It involves a radical. radical containing, what's that? Okay, the magnitude of the acceleration minus the result from part A, from the which is the tangential component of the acceleration. So if we have an addition of terms, most likely, and I've seen that before, we would have to compute an addition or subtraction. Well, that yeah, or subtraction of what's our rational expressions with different denominator, and that's going to be a big algebra problem. So I'm going to use the second version. Okay. So yes, it involves a cross product. I mean, it's still going to make us work a little bit. So, well, instead, so let me cross this because I'm not going to do it this way. Instead, I'm going to use the second alternative. That is the magnitude of the velocity crossed with the acceleration divided by the magnitude of the velocity. Careful, do not cube it. The cube is for calculating the curvature. Okay? I know the formulas look the same. All right. So we have the vectors v and a, that is velocity and acceleration. Let's get the cross product first. So v cross a, that is. Okay, let me write these two vectors. Oh, careful. You see the problem here? We have a vector valued function in R2 in 2 dimensions, and we are about to perform a cross product. So we cannot do it. What do we do? 0 for k, all right? So essentially, comma, 0, boom, close the angular bracket, right? Okay. So I, j, and k, that's going to be negative 6 sine 3t, 6 cosine 3t, 0, and okay, the second row is for the acceleration vector, negative 18 cosine 3t, negative 18 sine 3t, and 0. Okay. Let's repeat the first two columns. I'm going to do this cross product again one step at a time. Okay. So I'm not just going to give you the result. I, negative 6 sine 3t, negative 18 cosine 3t, 6 cosine 3t, negative 18 sine 3t. Like this, and all right, so let's do the cross product right here. Okay, I times 6 times 0, that's 0. J times 0 times negative 18 cosine, that's also 0. So that's going to leave us only with this 16 times 8, big number, that is 108. Positive, by the way, because negative times negative is positive. Sine squared 3t in the direction of k, minus whatever we get from the secondary diagonals, that is j times 6 sine times 0, oh, that's 0. I times 0 times negative 18 sine, oh, that's another 0, that's great. And another k times 6 times 18, that's going to be negative, first of all, minus negative another 108, but this time it's going to be cosine times cosine, that's cosine squared 3t, also k. So that's interesting because we have like terms and we have that identity again, sine squared plus cosine squared. So this vector will reduce really nicely. Number one, let me write this as minus minus equals to plus, that's 108 sine squared 3t plus 108 cosine squared 3t in the direction of k. And well, sine squared plus cosine squared, isn't that equal to 1 times the 108 they have in common? That's simply going to be 108 in the direction of k, which in component form I would do 0, 0, 108. Again, I would rather use component form because every time I see a number times one of the standard unit vectors, a very common mistake is to just write, oh, the first number we see 108, 0, 0. I've seen it before. So my advice, use component form. It'll be easier to read, it'll be easier to follow, and avoid those silly mistakes. Okay, so we have the cross product. That is the numerator, right? What else do we need? Oh, we also need the magnitude of the derivative of the velocity, which, didn't we find that in the previous part? Which is, what's that? Okay, that's actually 6, so we actually have it. Okay, so we may go ahead and write a sub n, that is the normal component, that is how much of the acceleration it's projecting onto the unit normal vector. That is the magnitude of v cross a that we just found in the previous part, divided by the magnitude of v, which we found in part 1. Okay, so that is, oh, I need the magnitude of this, right? The magnitude of v cross a, that is the square root of 0 squared plus 0 squared plus 108 squared. Don't waste time squaring the 108 squared because this is going to give us the square root of 108 squared, which is simply 108. That is 108 over 6, which equals 18. Okay, so let's write our expression to decompose the acceleration into these two vectors. That is, okay, so the acceleration, which is a linear combination of the tangential plus a linear plus of the tangential and a term for the normal, that is a sub n plus a sub t, a sub t and a sub n. Okay, that equals okay, so a sub t, what's that? So wasn't that a 0 times big T plus a sub n, which is 18 big N. All right, so that is a magnitude of 18 units of the it's projected onto the normal vector, while 0 for the tangential. Let's make sense out of this result, of course, because all this crunching of numbers and symbols and cross products, all this for what? Well, okay, let's have a look at this. Let me draw this a rough sketch of our vector valued function, which is actually it's a circular trajectory, right? We already mentioned that. So that's a circle, okay? So think of all these vector situations for this vector valued function. Well, let's talk about, okay, let me go to a random point, any point. That is this point, for instance. And I'm going to trace the, oh, hold on. Give me 1 second. I need to verify something real quick. Okay, yes, cosine and sine. That means it's going to be, it's going to go counterclockwise. So that means it's going to be directed in this direction. How do we know? Again, because we have the cosine in the x directions and in the x direction and the sine in the y direction. So that's going to be the unit tangent vector, okay? And big T, just to indicate the direction of the velocity vectors, all right? Now, what about at this point, where should I point the normal vector? Inside, right? That is big N. All right. Now here is the thing again. Where is the acceleration going to go? The acceleration also goes in the concave side of the graph, right? Now here is the thing. Okay, let me do the following. So this is also the acceleration. Remember, the acceleration is parallel to the position vector. So now, did you see how that acceleration vector I did in purple, it's overlapping the n vector, the unit normal vector? That explains the 18 here. Now, think of this vector. So if the sun is here, Is this vector projecting a shadow onto the tangential vector? I mean, this vector is orthogonal. This acceleration is orthogonal to the tangential, the unit tangent vector. It forms a 90 degrees. That means there's no shadow at all of this acceleration in the direction of the tangential. That explains this 0 right here. All right? So what are we doing? Expressing the acceleration as a linear combination of tangential and of unit tangent vector and unit normal vector.